Alrighty, good morning, guys. Welcome back to MAC 1140. I just got back from the dog park with my puppy, so I'm going to need just 1 second to kind of get things wrangled. So last time we talked about average rates of change. Oh, there we go. Today, I want to touch a little bit more on average rates of change. I want to answer a question that we kind of got close to talking about at the end of class on Tuesday. And then we're going to start talking about transformations. So this, as always, is MAC 1140. Section 008, which is pre-calculus. And today is the 9th of September, 2021. Today, we're going to talk a bit more on average rates of change, which was section 2.4, right? And then we jump over section 2.5 and we move to section 2.6, which is on transformations of graphs. So this is where we're going to start getting really into graphing functions. And I warned you, I think, on Tuesday, that for the 2.6 material, the transformations material, you really need to be comfortable with these parent functions, or sort of basic graphs, the graphs that are sort of the foundation of the shape of most of the functions we're going to play with in this class. Like this is 1 over x squared, the 4th root of x, the 3rd root of x, x to the 4, stuff like that. So we're going to kind of begin with these as our foundation, and we will slide them left, right, up, down, flip them over, stretch them out, all that good stuff. But first, I want to ask and answer a question from section 2.4 that we kind of walked right up to the line with, but then held back. So let me begin here by saying recall. Recall that the average rate of change for the function f from x equals a to x equals b is the slope. It's the slope of the secant line connecting the points a comma f of a with b comma f of b, which is f of b minus f of a divided by b minus a, which is like the net change from last week, net change, divided by the length of the interval AB. So it's kind of like, how much did you change divided by how long did you spend doing that change? And the examples we saw were like distance over time, that's a speed or a velocity. And the geometry here, I'll just sketch really quickly. We went through this in detail last time. If B is over here and A is over here, and the slope of this secant line is our guy, right? That slope is the average rate of change. Okay. You've had plenty of problems to work on this, and I trust that everybody is fairly comfortable looking at expressions of this form, simplifying them, evaluating them, doing the necessary bits of algebra. The question I want to wrap up this section with is, actually, before I ask the question, let me give you we'll call it a fact. It's like a theorem, but not quite as useful, just a fact. really it's a fact in two parts. If f is increasing on the open interval AB, then the average rate of change over that interval has to be positive. That's fact the first. And fact the second is that if f is decreasing on the open interval from A to B, so picture something like this. Do this over here. This over here. Then that average rate of change has to be negative. And you can see that just by thinking about the slopes of the secant line, right? Here, the secant line has to have negative slopes. So this means that the average rate of change is necessarily negative. And the question is, well, what about the converse? So if I turn these questions around, if the average rate of change is positive, does that mean the function has to be increasing? And if the average rate of change is negative, does that mean the function has to be decreasing? This is kind of getting at something in logic called an implication. And the question is this a one-way implication or is this a two-way implication? A good answer to this question would involve some calculus because it kind of has to do with how far apart A and B are. But if we think about a fixed interval of a particular length, A and B are fixed constants, is it possible that the average rate of change could be positive even if the function isn't always increasing on that interval? What's the most we can say? So I'd like to hear your thoughts on this question. So the question is the converse true? Does the average rate of change being, for example, being positive, force f to be increasing? And of course, we mean on the interval AB. So let's just look at this case right here and ask, can we turn this around? If f is increasing everywhere on the open interval AB, then the average rate of change from A to B has to be positive. That's true. Because if f is increasing, then this point has to be higher than this point. Every point as you go to the right has to be getting higher and higher and higher. And that means that the secant line will necessarily look something like this. It'll be lower on the left than it is on the right. And that's what it means to say the average rate of change is positive, because the average rate of change is the slope of the secant line. And if you look carefully at the picture I've drawn up here, you can actually find an answer to this question. So what are your thoughts? Genuinely want to hear what you guys are thinking.
Would it be no?
That's correct. Yeah. It is not necessarily true that a positive average rate of change means your function is increasing everywhere on the interval A to B. And the counterexample, one of them is drawn right there in the top right corner of the screen. That function is not increasing everywhere from A to B. Right? If we look right here, he turns around and starts decreasing a little bit. And we can think of a more extreme example. And the question for positivity and increasing is the same as the answer for negativity and decreasing. Both are no. The function f may have a positive average rate of change, but not be in, say, from x equals a to x equals b. Let's be very careful, but not be increasing everywhere on the interval a to b. And you know, a nice extreme counterexample. So something like, yeah, let's do something like this. So maybe a is over here. Maybe b is over here. So that average rate of change there, that's the slope of this line, which is certainly a positive slope. So that average rate of change is definitely positive, but this function is increasing, 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 decreasing, 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 increasing, increasing, increasing. So kind of what is the most we can say? We can say if your average rate of change is positive, then you've done more increasing than decreasing from A to B. That's about it, right? And the other way around, just change positive to negative, increasing to decreasing. If your average rate of change is negative, then we can say you've gone down more than you've gone up, but we can't say that you must have gone only down, right? It's possible for the function to start very low, come up high, turn around, come back down, and then go back up and end up higher than he started. And that's the condition that gives us the positive average rate of change. But certainly the function is not increasing from here to here. This function would be decreasing on this interval of x values here. Okay. That really wraps up the average rate of change section. That's everything you guys need from section 2.4. And I believe your homework associated with that section came due today at the start of class. If you do need more time on that, it's 9-9. Right, 2-4, yeah. Okay, so if you need more time on that homework 4, the one that was open between Tuesday and today, just go ahead and submit an extension request. I'll clear them out this afternoon. Because we are going to move on. You're going to have another homework set over the weekend between now and Tuesday. And the content of that is transformations of graphs. Which is section 2.6. We skip over 2.5. 2.5 is on linear models. It's boring, and God knows you got plenty of that shit in college algebra. One of the things that causes calculus students a lot of headaches, I see it in my Calc 2 classes, and it's rampant in my Calc 1 classes, is students who really don't know how to graph functions by hand. Even kind of what I would consider very basic functions that you should have in your head as examples and counterexamples all the time, thinking about whether this statement is true or false. Oh, well, think of this function. One of my goals here at Santa Fe is to remedy that problem. And the most useful tool I have to remedy that problem is to drill hard on this section. Because if you know those basic parent functions that I showed you in Desmos, and you understand the transformation rules that I'm about to show you now, you'll be able to graph 99% of the functions you're going to encounter in the calculus textbook. So the big idea here is by knowing the graphs of the basic parent functions, those graphs I showed you in Desmos, we can obtain graphs of many, many functions. And what's more, as you learn new parent functions like exponential functions, logarithm functions, these transformation rules will work for them as well. So what this does is it allows you to go from knowing one graph to knowing an infinite family of graphs. And the rules are fairly simple, but some of them are a bit counterintuitive. So to kind of introduce you to this, I'd like to look at an example, and we're going to approach it in the way that an 8th grader would approach it. We're going to plot some points, and then we'll start trying to make connections. And then eventually I will give you a list of rules that you'll have to remember. Okay. We're going to start with some basic functions, and we're going to move them around the plane. Shift them left, shift them right, squish them down vertically, shift them out horizontally, whatever. All right. Example. Sketch. Graph. F of x equals x plus 2 all squared. And we're going to do this by plotting points. So I'll make a little table. X's and Y's, X's and F of X's. We're getting used to this function notation. And I'll start at like -4, -3, -2, -1, 0. Let's just do these for now. And you'll see why I chose those particular numbers in a second. Obviously skewed towards the negative. If I plug -4 in for x here, then this will be -4 plus 2 all squared. -4 plus 2 is -2. -2 squared is +4. So f of -4 is +4. If I plug -3 into this function, I'll have -3 plus 2 all squared. -3 plus 2 is -1. -1 squared is +1. If I plug -2 in for x here, -2 plus 2 is 0. 0 squared is 0. If I plug -1 in here, -1 plus 2 is +1. 1 squared is 1. You plug in 0, you get 0 plus 2 all squared, which is 4. And if I plug in +1, I'll have 1 plus 2 or 3 squared, which is 9. So the graph of this function we have -4, 4. And I'll mark this as 4 here somewhere. So -4, 4 is right here. -3, 1. That's 4. 1 is here's half. Here. -2, 0 is here. -1, 1 is here. 0, 4 is here, and +1, 9 would be right up here. We have a nice smooth curve connecting these points. Something like this. Hopefully you all remember from previous classes, this is a quadratic function, so the shape of the graph is this parabolic shape. The vertex here is -2, 0. She opens up. That's about all you need to get a good graph of this. I'd like to compare this to another graph. I'll call that other graph g of x, that other function g of x, and we'll look at the graph of g of x equals x squared. And this is going around my way. I need to sketch it. This is a parent function. What's the relationship between these? Oh, I'm getting a call from Santa Fe. Sorry. So compare these two and tell me what the relationship is. Oh, and the hang up.
Is it the square?
Well, certainly they're both quadratics, right? We've got an x squared here. We've got some x stuff being squared here. What if I set the blue graph on top of the black graph? Maybe that will help. So,
Are all the points shifted to the left by 2?
yes, that's exactly it. So here's the blue graph overlaid with the black graph. Who was that? Is that Jimmy?
Yes.
Yeah, so if I take the blue graph and I shift it to the left 2 units, I get the black graph. Or if I take the black graph and shift it right 2 units, I get the blue graph. That's the big observation. So you can get the graph of f of x equals x plus 2 all squared by shifting the graph u of x equals x squared to the left by 2 units. And if you look at the algebra, the definition of the function f, there is a thing in there that clues you in, right? And we know it's okay, if there's a left shift 2, well, I got a 2 here. And those things are connected in the way they appear to be connected. What this is hinting at is our first transformation rule. And that's that adding and subtracting on the inside of a function. Everywhere you have an x in the original, replace it by x plus 2. That will shift that graph to the left by 2 units. If I replaced x everywhere by x minus 3, that would shift it to the right by 3 units. So if you know the graph of x squared, you can get the graph of any function that looks kind of like this, right? Like x plus 5 squared would be shifted to the left 5 units. Let's see if we can just run with this for a minute. I haven't even written down the rule yet, but you all have already learned it. All right. I want to sketch the graph of y equals x plus 3 all squared and y equals x minus 4 all squared. And I'm going to do it without making a table. So I'm going to begin with my parent function g of x equals x squared, which I know looks like this. All right, everybody knows this graph, yeah? So I've got -1, 1, +1, 1, -2, 4, +2, 4, 0, 0, right? There's your x squared graph. How am I going to get this first one?
Would you move the vertex to the left?
Yes, and not just the vertex, but everything. But you can think of it as like the vertex is kind of the root here, right? And so as he moves, everybody else moves. Yeah, that's exactly correct. So we're going to shift g of x left by 3 units to get y equals x plus 3 squared. And you might ask, why is that the rule? Why is adding 3 on the inside shifting me left? Isn't adding 3 like going to the right? But you have to think about what input is necessary to get the output 0, say. So in the original, g of x equals x squared, if you plug in x equals 0, you'll get 0 out, and that's your vertex. To get 0 out from this guy, the inside of these parentheses needs to be 0. And the only way to do that is to make x -3. So adding 3 on the inside moves you to the left by 3, which is exactly what we said. And what's neat is that all the other points move along with it. So this point, 1, 1, if I move him to the left 3, he's going to become -2, 1. And this point, -1, 1, if I move him to the left 3, he's going to become -4, 1. We just have to kind of think spatially. You have to really imagine literally picking up the graph and moving it around. All right, and that's an acceptable graph right there. If I mark this height here as 1, we've got 1, 2, 3 points that we know are on that graph. And that's the standard I'm going to hold you guys to. So on the test, when I ask you graph this using transformations, I'll have you sketch the original graph, labeling 3 points explicitly. And then you'll sketch your transformed graph, labeling those same 3 points, like where they end up under the transformation. So the point -1, 1 gets mapped to -4, 1. The point 0, 0 gets mapped to -3, 0. And the point 1, 1 gets mapped to -2, 1. So I got a question in chat asking about symmetries. And yeah, remember quadratic functions, functions that can be written as like ax squared plus bx plus c, they always have an axis of symmetry. So it's true that the symmetry which exists here will necessarily exist here, just about a different line. So that symmetry, you may have seen this term in your algebra classes of yours. This line here is called the axis of symmetry for that parabola. Because if you were to fold this guy up like a book along that, the graph would sit right on top of itself. Here, the axis of symmetry moves with the graph. So yes, Chris, that is a true statement. All right, let's try the other one. Okay. So how am I, starting with x squared, going to get quantity x minus 4 squared? Because this is so similar to this, it's reasonable for us to think it's going to be a shift of some sort. one direction or another, left, right, up, down, by some number of units. And I encourage you to think about the vertex. So what input would be necessary here to get the output 0? I got a good message in chat there saying the parabola starts at 4. I caution you against using language like that, like saying the graph starts at this or that, because it's a little bit imprecise. But I think I know what you're thinking, and I think you're correct. But let's be a little bit more precise. What exactly should I do to every point on this graph to turn that into the graph of this function?
Move it to the right by 4.
Very good. We're going to move every single point on the graph of x squared to the right by 4 units. Since we go to the right by 4 units. That's because in order to get 0 out of this, x would have to be 4. And then you just draw that same shape. These 3 points kind of clustered around the vertex form a nice sort of backbone for this parabola. We can use those. This would be 3, 1, and this would be 5, 1. See, this ain't so bad, right? Okay. Let's look at one more example here where we're using a different parent function. First, are there any questions on what we've done right here? If you want to draw on the axis of symmetry here, it would be this guy. Okay. All right, so we're going to start testing your familiarity with the parent function graphs here in just a little bit. But I want to start off this portion the same way we did last time. I'm going to give you some sort of transformed graph. We're going to sketch it by plotting points and then compare to the suspected parent function. So again, we're making a table. What's the domain of this function? Recordings are always posted to Canvas under the announcements. The same announcement you found the link to this Zoom meeting will have the link to the recording as soon as it's uploaded. What is the domain of this function?
Would it be all real numbers except it can't equal -2?
So what domain, not quite, what domain red flags do we have here?
It can't be a negative.
Yeah, I've got some variables under a square root. So I know that the stuff under the square root isn't allowed to be negative. And I think I get, was that, I'm not sure who the last answer was, I'm sorry. But I think the +2 is not under the square root. The square root stops right here. So thing we need to watch out for is making sure that we don't have any negatives under this root. Well, the only thing that's under this root is x, right? So a quick note here, the domain is just x is greater than or equal to 0, i.e. bullet-shaped interval 0 to infinity. So I'm not going to go plugging in negative numbers here. I'll just start at 0. I'm also going to use perfect squares because I know the first step I need to do in plugging in here is take the square root. So I'm going to skip over 2 and 3, go to 4, and then 9. F of 0 is the square root of 0 plus 2. All right, and again, the plus 2 is outside the square root. So the square root of 0 is 0. 0 plus 2 is 2. So f of 0 is 2. F of 1 is the square root of 1 plus 2. And the square root of 1 is 1. So that's 1 plus 2, which is 3. F of 4 is the square root of 4 plus 2. The square root of 4 is 2. 2 plus 2 is 4. And f of 9 is the square root of 9 plus 2. Well, the square root of 9 is 3, so that's 3 plus 2, which is 5. Okay. So I need to come out to 9. And 1. All right. And then on my vertical axis, just make sure I include all those outputs. So when x is 0, f of 0 is 2. That means I have the point 0, comma 2 on this graph. When x is 1, y is equal to 3. That's right here. When x is 4, y is equal to 4. So that's here. And when x is 9, y is equal to 5. That's here. So the shape of this graph, I'll do my best to draw this in a way that's not hideously ugly. It's like this. Nice big fat points, right? Big fat points, that's fine. Oh. Really what this is it's half of a sideways parabola, if you're wondering, right? If you turn it like this, that looks like half of a parabola. This thing is half of a sideways parabola. Actually, literally, like not it's like that, it is that. What does the graph of the square root of x on its own look like?
Would it start from the origin?
Yes, but again, I'll say, let's
Be
speak
shifted down to?
language like that. Yeah, let's describe exactly what happens. So this guy goes through 0, 0, 1, 1, 4, 2, and 9, comma 3. Like this. So what would I do to the blue to get the purple? I would move it up by 2 units. So to get the graph of f of x equals square root of x plus 2, from g of x equals square root of x, we shift the graph of g up by 2 units. So we saw adding and subtracting numbers kind of on the inside of our function moves things left and right. Adding and subtracting numbers on the outside of my function will move things up and down. To take
I have a question.
Sorry, yeah, go ahead.
So was the reason why you stopped it like at the y like being 0, was that because the domain?
Right. Yeah, the domain here is just
Okay.
to infinity. So I can't have anything over here to the left because those are all negative x values. And there isn't anything down here, like on the purple graph, or you ask why it doesn't continue like this. Because that wouldn't be a function, right? When I plug in 1 for x, I only get one number out. I only get 3 out. So 1, 3 is the only point on the graph here. Whose x coordinate is 1. For this parabola to like continue to have 2 sides like that, I would have to output 2 values with the input 1. Now there is something to what you're asking. So here's the parent function we're playing with, y equals square root x. Look at y equals negative square root x. There's the other half. But for us, the square root function always returns the positive square root. Okay, so to get the purple graph from the blue graph, you move the blue graph up 2 units. And again, there's kind of a hint, right? This is +2 and it's on the outside. So let's see if we can use this intuition to sketch some other graphs. And in this last guy, I'm going to combine the thing that we talked about before, left and right stuff, with the thing that we're doing now, up and down stuff. All right. To get y equals square root of x minus 3, with the minus 3 outside the square root, we're going to shift the parent function g of x equals the square root of x. How? Up, down, left, right, and by how much? Think about it. I'm gonna grab some more. All right, so what are we going to do?
If you start at the point of origin, would you shift it down to shift it down 3, so it'd be in the -3?
Very good. All right, if I take this original graph, the blue dotted graph here, and I move every point down by 3 units, that will give me this guy. And this is fairly intuitive. Look at what we're doing. If you take y equals square root x, This says subtract 3 from all of those y values. Well, what happens if you subtract from the y values? Things go down. So 0, 0 is going to go down to 0, -3. 1, 1 is going to go down to 1, -2. Four, 2 is going to go down to 4, -1. And 9, 3 is going to go down to 9, 0. So this curve is going to look like this. It doesn't have to be perfect, but there you go. It's that same basic square root shape. It's that half of a sideways parabola thing, just shifted down. And again, it can be thought of intuitively. The vertical shifts are actually quite intuitive because you've got y equals the square root of x minus 3. Well, that minus 3 just says subtract 3 from all the y values on the square root of x graph. The next one I'm going to do on the other page. So let's continue this. Over here. The guy we're trying to graph is the square root of x plus 2 minus 1. That has two things going on. Again, what we're trying to do here, continuing the previous example, is sketch y equals the square root of x plus 2 minus 1 without making a table. And we're going to start with our basic square root graph, the parent function, that's what we call it. G of x, square root of x, and I'll sketch that again for you quickly here. Looks like this. 0, 0, 1, 1, 4, 2, and so on. All right, so we'll just use these 3 points. That's enough. What sort of transformations do you think I need to apply to g of x to get this guy? Because here there's something going on inside the square root and something going on outside the square root.
You have to shift down -1 and then shift to the left 2.
Those are the correct transformations, yes. Beautiful. Who's that? Genesis, very nice. Now I'm gonna alter what you said just a tiny little bit. So Genesis said we need to shift down 1 and left 2. Here's a question. Is that the same as shifting left 2 and then down 1?
Yes.
Yeah, if I move this to the left 2 units and then down 1 unit, I will get the same thing as if I moved down 1 unit and then to the left 2 units. Now, bad news time. That's not always true. It's true here. And I'll give you very specific rules about this, but sometimes the order of transformations matters. So the rule I'm going to give you is that you always do horizontal stuff before vertical stuff. And you always do what are called scalings before any shifts. Now, we haven't talked about any scalings yet, so you don't need to worry about it for now. Let's go ahead and sketch this graph because what you said is perfect. Want to go left 2 and then down 1. Left 2 and then down 1. So 0, 0 gets mapped over here to -2, comma, -1. And then we just draw that same shape. And it doesn't have to be perfect, but you should be able to follow a few points. The point 1, comma 1 gets mapped here to -1, comma 0. And the point 4, comma 2, if we drag this left 2, then its x coordinate will become 2. And if we then bring that down by 1, the y coordinate will become +1. So this becomes 2, comma 1. There we go. That's it. This is our graph. So we shift left by 2 units and down by 1 unit. Okay. So those are the first two kind of fundamental transformations, horizontal shifts and vertical shifts. They're both shifts, right? And there's one horizontal, one vertical. The other kind of transformation is called a scaling. Some people talk about like stretch and compress. I think the word scaling is perfect for this because scaling can mean both of those things. And like the shifts, there are horizontal scalings and vertical scalings. Let's use a different parent function again. Okay, I'm going to sketch the graph y equals 1/2 times the absolute value of x by plotting some points. I see there's another question in the chat here, so let me. Okay, yeah, so a couple questions in chat. This transformed function that we just finished working with, the domain is indeed -2 to infinity. That's correct. So as we shift left and right, our domains change. And as we shift up and down, our ranges change. So the domain and range of the original function here were both 0 to infinity. The domain of the transformed function is -2 to infinity, and the range of the transformed function is -1 to infinity. So both the domain and range change. That's correct. And your domain is perfect. And then Christopher, yeah, the x squared graph and square root of x graphs are definitely different. I would again caution like saying things like the graph starts. Like this graph doesn't really start anywhere. I could say it starts here and it goes left over that way and it goes right over that way. Or here, some people might say this graph starts at -1 because that's where the y values become positive, but it also goes to the left like this. So I'd like to give a good answer to your question, Chris, but I'm not entirely sure I understand it. X squared plus 2 would be shifted up 2. We would take x squared and shift it up 2. Megan, it's correct that the general guideline I'm going to offer is to always do horizontal stuff before vertical stuff, and then to do what are called scalings, which we're about to see our first one of here, scalings before doing any shifting. But
Okay.
I'll lay those rules out very, very clearly in just a minute. I just want to play with these a little bit more. It's nice to have a few victories under your belt before you look at those scary rules altogether. So let's do it. Let's sketch this guy by plotting points. Oh, and I've been calling these. Let me do this sometime. It's f of x, right? Okay, let's do that. So here's my table, x comma f of x. And let's look at like -4, -3, -2, -1, 0, 1, 2, 3, 4. All right, big table here. You'll see why. If I plug in -4 for x, then that's the absolute value of -4, which is +4, times 1/2, which is +2. If I plug in -3 for x here, I get the absolute value of -3, which is +3, times 1/2, which is 3/2, or 1.5. If I plug in -2, I get +2 times 1/2, which is 1. If I plug in -1, I get absolute value -1 is 1 times 1/2 is +1/2. 0 gives me 1/2 times 0. And then there's symmetry here. 1/2, 1, 3/2, and 2. So we've got some fractions now, but that's okay. It's not going to hurt us. All right. And then it's 1, 2, 3, 4, something like that. Okay. -4, 2 is on this graph. -3, 3/2. I'll skip that one. We'll come back and look at it. Let's just do the nice ones. So -2, 1. 0, 0. 2, 1. And 4, 2. And the difference between this and the sort of parabolic stuff is that this is made up of straight line pieces. And I would say we should compare this sort of what's the real controlling thing here? It's the absolute value of x, whose graph looks like this. Oh, I should have dotted this, didn't I? Do dotted lines in the other one. That's okay. Okay. So what's the relationship between the blue graph and the purple graph? Well, if you take the height of every point on the blue graph and you chop it in half, you get the height of that point on the purple graph, right? Look right here at -4. If I bring this guy down by half, I get this guy. If I bring this guy down by half, I get this guy. If I bring the 1 down by half, I get 1/2, which is the y value here, right? -1.5. And the same is true over here. If I take the point on the blue graph and I bring it down by 1/2, I get the point on the purple graph. I take the point on the blue graph, bring it down by 1/2, get the point on the purple graph. You get the picture. So to get y equals 1/2 times the absolute value of x from y equals absolute value of x itself, we squish it vertically. And the term for that is we just say we scale vertically by a factor of 1/2. What this means is that you divide all the x values or divide all the y values by 2. And multiply all the y values by 1/2. So you take all the y values on the graph of the blue function, multiply them by 1/2, keeping the x values alone, leaving them the same. That will give you the graph of the purple function. This is called a vertical scaling. Scale, right? Everybody has an idea of what the word scale means. When you talk about like, I'm gonna scale this up, or I'm gonna scale this back, economies of scale, or a 5th scale model. All of those things mean you take the thing and you shrink it, or you take the thing and you stretch it, you enlarge it. So scaling is just to like leave the shape alone, but embiggen or enlittlen the thing in one dimension or another. So here what we've done is we've scaled vertically. Right? That's the vibe. And there's a difference between a vertical scaling and a vertical shift. If I shifted the purple graph up by 2, or I shifted the blue graph down by 2 or something like that, they would not turn into each other, right? If I take the blue graph and I say I'm going to shift it down by 1/2, it's going to keep that same steepness. It's just going to go down like this. It won't like unfold the way we need it to. So there is a difference between a scaling and a shift. They're not the same operations. And unfortunately, it's scalings that don't commute well with each other. So the order is going to start to matter once we introduce vertical and horizontal scaling. Now, there are special forms of scalings called reflections. And I wanted to start blending some of these things together. Bad example for horizontal scaling, so let's not do that. Let's sketch y equals the negative of the absolute value of x minus 2 without making a table. Step 0, identify the parent function. So this bad boy's shape overall is going to come from the absolute value of x. That's the main thing going on here. And that's why I use the word parent function, right? Like we all have some features of our parents. Probably we all have a lot of features of our parents, but we're slightly different. This guy has a lot of the same features as this guy. This is the parent of this thing, but this thing is the next generation. It's a little different. So first, identify the parent function. Then we have to identify the particular transformations. And again, I've mashed a few of them together here for us to think about. What does the minus 2 on the inside do?
Does it shift it right?
Very good. That's a horizontal shift. It's a shift to the right by 2 units. This, the negative on the outside, it's playing the same role that the 1/2 played on the previous guy, right? And what that 1/2 did is it shrunk the y values all down by a factor of 2. Or by a factor of 1/2, right? Divided them all by 2, multiplied them all by 1/2. This is going to multiply all the y values by -1. What is that going to do?
flip the graph over the y-axis or x-axis?
Very good. It's going to flip the graph over the x-axis. This is going to be a vertical reflection. And to help you see that, just off to the side, let's look at a few points. I'm going to take a few points here, just a few, like 1, 2. Here's 1, 2. And if I change that y value to -2, he's down here. And that move is a flip over the x-axis, or a vertical reflection. If I look at 2, 1, and I compare that with 2, -1, again, flipped over the x-axis, vertically reflected. Okay, so multiplying all your y values by -1 flips everything over vertically. And remember the rule, horizontal stuff before vertical stuff, and scalings before shifts. So we've got two transformations here. There's a horizontal shift, and it's to the right by 2 units. And there's a vertical scaling, like the last one, but this one is a vertical flip. Flip over the x-axis. My advice to you is, as these problems get more complicated, and they will, do the transformations one at a time. Sketch several graphs. Start with the graph of the parent function, apply the transformations 1 or 2 at a time until you get to your final function. So I'm going to start with the graph of the absolute value of x. That's my parent function. And I'm going to label a few points like 0, 0, 1, 1, and -1, 1. And then one at a time, I'm going to apply those transformations. So horizontal stuff before vertical stuff, and within each of those categories, scalings before shifts. So horizontal stuff, I don't have any horizontal scalings, just a horizontal shift. So first I'll do that horizontal shift. That's to the right by 2 units. So here's 1, 2. And you track where each of those points go. 0, 0 goes to 2, 0. -1, 1, where does that go? Well, if I move that to the right, 1, 2, then that's going to go to 1, 1. And 1, 1, if I move that to the right, 1, 2, it's going to go to 2, 1. I'm sorry, 3, 1. And what graph is this? This is y equals the absolute value of x minus 2. So I haven't finished yet. Now my last move is this vertical scaling. So I'm going to take this graph and flip it over. So the point 2, 0, when you flip it over or multiply the y value by -1, he stays 2, 0. The point 1, 1, when you flip it over, becomes 1 comma negative 1. And the point 3 comma 1, when you flip it over, becomes 3 comma negative 1. So here is your final graph. This is the graph we wanted. This is y equals negative absolute value x minus 2. And besides plotting points, this is really the only way to get this. The absolute value is kind of like a box. It's hard to get things in or out of the absolute value box. Like I can't just pull this 2 out. There's no way to do that. I can't pull this negative in. There's not a nice way to do that either. So what I'm trying to do there actually is address the question that Megan asked in the chat. The absolute value of x minus 2, would that turn something positive? Well, yes, but it turns the output from x minus 2 positive. It doesn't turn the 2 itself positive. So a little note here maybe. The absolute value of x minus 2 is not x plus 2 or absolute x minus 2 or absolute x plus 2 or absolute x plus 2. Unfortunately, the absolute value function is kind of a tricky box, and there's really not much we can do with the tricky box, but look at what's inside and look what's outside. It is true that absolute values are a distance. You can think of the absolute value of x minus 2 as the distance from x to 2. And that way of thinking can be useful sometimes, but not especially useful here. It is true that the absolute value always outputs positive or non-negative things. And that does relate to the absolute value being a tool for measuring distance. That's certainly true. No, don't be sorry. These are exactly the sort of conversations we want to have. It might be worthwhile. Remember when we talked about the absolute value as a piecewise function? The absolute value of some stuff, call it u, is equal to that stuff if that stuff is greater than or equal to 0, and the negative of that stuff if that stuff is less than 0. And this means that the absolute value of x minus 2 is equal to x minus 2 if x minus 2 is greater than or equal to 0, and the negative of x minus 2 if x minus 2 is less than 0. And that can be rewritten as x minus 2 if x is greater than or equal to 2, and negative x plus 2 if x is less than 2. And if you look at this graph, to the right of 2, it looks like the function negative x plus 2, slope negative 1, the y-intercept would be up here at 2. And if you look for x's which are greater than or equal to 2, oh, that's not what we have graphed there. Sorry, this guy. Yeah, this guy behaves like x minus 2 if x is bigger than 2, and negative x plus 2 if x is less than 2. Very good. All right. Yeah, the piecewise definition of the absolute value function is really useful. And then homework extensions, you got to request them in WebAssign, right? Emails and Canvas messages and requests here in class are fine, but I'm not going to remember, and it goes much faster, much cleaner. Please just put in the extension request in WebAssign. I will grant it. All right. So horizontal shifts, vertical shifts, and vertical scalings. There's one missing, a horizontal scaling. Let's look at him. I kind of wish we had more parent functions to play with. Let's sketch There's a few we haven't messed with yet. F of x equals maybe a cube root. Sure. Or well, let's do a cubing function maybe. No, let's do a cube root. Yeah, let's do a cube root of 2x by plotting points. All right. So again, plotting points this time, just making a table. What's the domain of this function? Does this function have any domain red flags?
Is it x has to be equal to or greater than 0?
So if this was a square root, I would need this stuff to be greater than or equal to 0. But since this is a cube root, it's an odd root, not an even root. There's no red flags. Domain is all real numbers. But if it were an even root, like a square root or a fourth root, then yeah, 0 to infinity. All right, I'm going to pick some x values to plug in here. I'm going to pick them kind of carefully. -4, -1/2, 0, 1/2, and +4. I'm choosing those to make sure that the outputs are nice. If I plug -4 into this function, then the inside here would be 2 times -4, that's -8. What's the cube root of -8?
2.
-2.
Yeah, -2. If I plug -1/2 in here, then I have the cube root of -1, which is -1. If I plug 0 in here, I have the cube root of 0, which is 0. If I plug 1/2 in there, I'll get cube root of 1, which is +1. And if I plug 4 in there, I'll get the cube root of 8, which is 3. Oh, sorry. Cube root of 8, which is 2. All right. So let's plot these points. Call this -4, so that's -2. What is that? 4, 2. So -4, 2. Is up here. Then 1/2, oh shit, fuck me. -4 and -2. I'm so sorry. Yeah, ignore this point. Please don't on your paper here. -4, -2. Ignore this guy. -1/2, comma, -1. Well, that's -4. This is -2. That's -1. So -1/2 is right here. So there's -1/2, comma, -1. 0, comma, 0 is right here. And here's 4, so this is 2, so this is 1. So +1/2, comma, 1 is right here. And then 4, comma, 2 is out here. So this curve has a very neat shape. And all odd root functions kind of have this shape to them. And if we want to compare this the natural parent function here is just the cube root of x, which goes through 0, 0, 1, 1, negative 1, negative 1. What else? Let's see, what's our next nice cube? It's 8, right? So that would be 8, comma 2, which would be, bring this way out. So now why I chose the scale I did. It's -8. And positive 8, something like that. So the blue graph this time I will do it dotted. Is much wider. In fact, the blue graph is wider by exactly a factor of 2. Does everybody see that? If I take, for example, this point, 8, comma 2, and I cut its x value in half, leaving its y value alone, that will drag me over to this guy, 4, comma 2, which is on the purple function. Or if I take this guy, -1, comma -1, and I cut his x value in half, that will drag him over here to -1/2, comma -1, which is the point on the purple graph. So what's the relationship? To get f of x equals the cube root of 2x from g of x equals the regular cube root of x, we scale horizontally by a factor of 1/2. And that's not immediately obvious looking at the algebra here. The fact that multiplying by 2 on the inside brings you in rather than stretching you out is, I think, a little counterintuitive. And sort of the moral of the story here is that horizontal stuff is all kind of the opposite of what you'd think, right? Like subtracting 2 on the inside moves you in the positive direction to the right. And adding 2 on the inside moves you in the negative direction to the left. Similarly, if you multiply by 2 on the inside, that doesn't stretch you out by 2, that squishes you in by 2, or squishes you in by a factor of 1/2. This shape is similar to x cubed. X cubed is like up and down rather than left and right. So if you turn this picture kind of like this, that's closer to x cubed. It is similar. They're inverse functions of each other. We'll talk about that a little later. So there's some asymmetry. But the parent function here is its own thing. The cube root of x is its own thing. It's its own parent function. It's not, the parent here is not x cubed. Okay. So we've now seen an example of all of these. I want to lay out the rules for you and then look at some complicated ones. So here are the rules for transforming graphs. Make sure these get somewhere into your notes nice and clean where you can refer back to them. Graph transformation rules. All right, remember we've got kind of 2 categories. Horizontal stuff . We have horizontal scaling and horizontal shifts. Then we have vertical scalings and vertical shifts. And you want to do them in this order, right? Look for horizontal scalings. If you don't have any, look for horizontal shifts. If you don't have any, look for vertical scalings. If you don't have any, look for vertical shifts. And if you have more than one of these, you need to do them in this order. If your function f of x is equal to the parent function g, but with some number multiplied on the inside, g of c times x, this scales the graph horizontally by 1 over c. That's kind of counterintuitive, but it's correct, right? Like multiplying by a 2 on the inside didn't stretch me out, it shrunk me in. The blue is the original. The purple is the transformed graph. So the purple is the cube root of 2x. Multiplying by a 2 on the inside didn't stretch the blue out further, it squished the blue in. Horizontal shifts, if your function f of x is g of x minus c, this shifts to the right by c. And if c is negative, that's like x plus c on the inside, then you're going to the left. That shifts left by c units. I'm assuming c is positive when we write it like this. Vertical scaling, if your function f of x is equal to some constant c times the parent function g of x, this scales the graph vertically by c units. So what do I mean when I say that? I mean, it multiplies all the y values by c. And what I mean here is that we multiply all the x values by 1 over c. So let me even make that clear. What do we mean exactly by this? We mean multiply the y values by c. And here, what do we mean? We mean multiply the x values by 1 over c. And then finally, the vertical shift. This is the easy one. If f of x is equal to g of x plus c, this shifts up by c units. And if f of x is g of x minus c, this shifts down by c units. How am I doing with time? 12:29. Oh, we gotta go. Alrighty, guys, I'm gonna go ahead and end the meeting here. I have another class starting in just 1 minute. So maybe take a screen cap if you need it. These are the rules. You do them in this order, okay? I am gonna publish a new homework for y'all a little later today. I see there's something else in chat. I want to clarify the homework due Tuesday on the quiz. There is a quiz due on Tuesday. There will also be another homework that I'm gonna publish today. Let's do Tuesday. The Discord is still active, but the invite link may have expired. So I will look and see if I can update that invite link. 7 wasn't posted, shortcuts. Yeah, I'll take a look and see if there's a missing recording from the past lectures and get those updated. All right, guys, I gotta run. Take care. I will see you all on Tuesday. Watch Weather Sign. You got stuff to do.
Thank you.
Of course.